Prepare to rethink what you know about Jupiter's core, because groundbreaking research is shaking up one of planetary science's biggest debates. For years, scientists believed that Jupiter's unusual interior was sculpted by a single, massive collision with a protoplanet. This dramatic theory suggested such a giant impact would have triggered enough chaos to thoroughly mix Jupiter's dense inner core with lighter outer layers, explaining the planet's mysterious, diluted center. But here's where things get controversial. Recent supercomputer simulations, led by researchers at Durham University, with collaborative input from NASA, SETI, and the University of Oslo, put that dramatic impact theory to the test. They pushed the simulations to the extreme, recreating the most cataclysmic planetary collisions imaginable. Yet time after time, the outcome didn't match what most expected. Instead of producing a gradual blended core known to scientists as a dilute core, the simulations consistently formed well-defined boundaries between heavy core materials and the vast surrounding ocean of hydrogen and helium. Even under the most violent conditions, the planet's interior simply refused to smooth out into Jupiter's actually observed dilute core. And this is the part most people miss. The research points to a much less dramatic, but far more subtle, origin story for Jupiter's interior. The team's findings suggest that rather than being the result of a rare, catastrophic crash, Jupiter's dilute core likely took shape gradually as the planet grew, gently and inexorably, collecting a mix of heavier and lighter elements over millions of years. This process, called accretion, could naturally blur the core's boundaries, creating the smoother, diffuse layer that later rival missions like NASA's Juno detected. But the story doesn't stop with Jupiter. Evidence is mounting that Saturn harbors a similar dilute core. If two gas giants in our solar system evolved this way, is it possible that most giant planets throughout the universe have a comparably complex internal makeup? If this theory holds true, it throws a wrench into the idea that only extraordinary collisions shape planetary interiors. Instead, it hints that the universe might prefer slower, more intricate processes to create its most massive worlds. Thomas Sanders, the study's lead author, put it plainly. It's fascinating to explore how a giant planet like Jupiter would respond to one of the most violent events a growing planet can experience. We see in our simulations that this kind of impact literally shakes the planet to its core, just not in the right way to explain the interior of Jupiter that we see today. And as Luis Teodoro of the University of Oslo commented, the fact that Saturn shows the same blurred internal structure further tips the scales away from the cataclysmic impact explanation. But here's a bold question for you. Could everything we thought we knew about the early violence of planet formation be overstated? Are slow, quiet accumulations of matter just as important, if not more so, than the headline-grabbing cosmic collisions? And what does this mean for the many exoplanets orbiting other stars? Are their secrets hidden in gradual evolution rather than dramatic events? Jacob Kegereis, another co-author, summed it up best. Giant impacts are a key part of many planets' histories, but they can't explain everything. His team's ongoing efforts to refine impact simulation techniques will continue to peel back the layers on how our solar system and others like it came to be so diverse and complex. So what do you think? Does this new evidence convince you that planetary cores form gradually, or do you still favour the old giant impact model? Which side of the debate are you on, and why? Join the conversation. Your thoughts might just help redefine our understanding of how worlds like Jupiter are born.